This is my second lecture on multicollinearity, and in the previous lecture we have learned what is multicollinearity. The problem of multicollinearity arises when two or more than two regressors variable are linearly dependent. Today basically we are in the last class also we talked about the presence of multicollinearity has severe effect on least square estimates of regression coefficients. Today again we will talk about the effects of multicollinearity or the problems due to multicollinearity, and also we will learn how to detect the presence of multicollinearity in the data. Okay, so let me first talk about some more problems due to multicollinearity. Okay, in the last class we proved or we illustrated the fact that the strong multicollinearity results in large variance and covariance of the regression coefficients. Okay, so we illustrated this issue using in the case of multiple linear regression when there are two regressors in the multiple linear regression model, and also in general we have proved this fact that the strong multicollinearity results in large variance and covariance of regression coefficients. And today we will be talking about some more problems due to multicollinearity. The second one is multicollinearity tends to produce least square estimate beta hat that are too far from the true parameter. Beta. Okay, so here we compute the square distance between the least square estimate of the regression coefficient beta I hat minus beta I. So, this is the estimate of the ith regressor coefficient, and this is the true value of the ith regression coefficient, and the square distance is this one, and sum over I is from 1 to k minus 1, right, and we denote this by L square. Okay, next what we do is this is the square distance from beta hat to the true parameter value beta. Okay. Next we compute the expected value of this square distance. So, expected square distance we denote it, this is basically expectation of L square, which is equal to expectation of beta I hat minus beta I square sum over all I right. Well, what we know is that this beta I hat is the least square estimate of beta I, and we know that the least square estimates are unbiased estimated here. So, we know that expected value of beta I hat is equal to beta I. So, this one is nothing but expected value of beta I hat minus expectation of beta I hat, right, and this one is nothing but the variance of beta I hat, variance of beta I hat. Okay. Now, the variance of beta I hat in multiple linear regression model is equal to summation sigma square x prime x inverse the ith element, okay, and this one is equal to sigma square by the ith element, which we proved before also, it is 1 minus r I square, okay, sum over I. So, this one is basically sigma square sum 1 by 1 minus r I square. Okay. So, this r I square is the coefficient of multiple determination, where r I square is the coefficient of multiple determination for the regression of x I on the remaining k minus 2 regressors. Okay. And also so what we proved is that expected value of this squared distance E L square is equal to sigma square sum 1 by 1 minus r I square sum over I, and when there is multicollinearity, one by 1 minus r I square will be large for at least 1 I. Okay. Well, so this Ri square is the coefficient of multiple determination for the regression of x I on the remaining k minus 2 regressors. Now, you know, multicollinearity means the problem of multicollinearity arises when two or more regressors are linearly dependent. Now, if say for example, if the ith regressor x I is linearly dependent on the remaining regressors, then R I square, the coefficient of multiple determination associated with x I is close to unity. That means, R I square will tend to 1. When R I square will tend to 1, then 1 by 1 minus R I square will tend to infinity, and then the expected value will be that is why it says that when there is multicollinearity, this term will be large for at least one I. So, it depends on if x I is linearly dependent on the remaining regressors, then this term will be large, and this term is large means R I is close to when 1 by 1 minus R I square will tend to infinity as R I square tends to 1. Okay. Well, so next we will talk about some more problems due to multicollinearity, that is the model coefficient with negative sign when positive sign is expected. Well, so that it says that you may get negative sign for some regression coefficients when you expect you are really expecting that positive sign for that regression coefficients. So, this might be the effect of multicollinearity. And the next issue is say 4, it says that high significance in a global F test but in which none of the regressor are significant in partial F test. Okay, so I like to illustrate this point also. It says that high significance in the global F test, but none of the regressors are significant in partial F test. So, for this one I want to recall one example from multiple linear regression model. okay, I mean there is only one example in I mean I talked about in module 2, that means in the multiple linear regression model. I am going to recall that example. So, here is the data, I mean, or here is the example we considered in module 2, multiple linear regression model. Well, so here we have two regressors and one response variable, and we have the data for that. Well, we know how to fit a multiple linear regression model here. The fitted model, if you can recall, the fitted model is y hat equal to 14 minus 2 x 1 minus x 2 by 2. Now, once we have the fitted model, what we do is that we check the significance of the fitted model by using the global test. That means, we test the hypothesis that beta 1 equal to beta 2 equal to 0 against the alternative hypothesis that H naught is not true. So, the significance of the null hypothesis that beta 1 equal to beta 2 equal to 0, it says that there is no linear relationship between the response variable and the regressor variables. And we test this hypothesis using the global f value that is obtained from the ANOVA table. So, here is my ANOVA table for this data. Okay. You just refer my classes in module 2. Well, so we have perhaps 11 data, and that is why the total degree of freedom is 10, and the f value is 7.17, and this f follows f distribution with degree of freedom 2 and 8, right. And since the observed f value is larger, I mean greater than the tabulated f value, we reject the null hypothesis beta 1 equal to beta 2 equal to 0, and that means we accept the alternative hypothesis, that is beta 1, okay, beta I is not equal to 0 for at least 1 I. Okay, so the ultimate conclusion from this test is that the fitted model is significant. So, the global test says you reject the null hypothesis, where the null hypothesis is it says that there is no linear relationship between the response variable and the regressor variable. So, we are rejecting that null hypothesis. That means, we are accepting the fact that there is a linear relationship between the response variable and the regressor variables. Now, we go for the partial F test. So, here is my partial F test. The first, it says that what does x 2 contributes given that x 1 is already in the regression. Okay. So, the contribution of x 2 in the presence of x 1 is whether the contribution is significant, that can be tested by testing the hypothesis that beta 2 equal to 0 against beta 2 is not equal to 0. So, this one basically it test the significance of x2 in the presence of x1 in the regression model. And you know, either you can go for the partial F test or you can go for the t test to test this hypothesis. Well, so here I took the t statistic approach. Here the t value is this one. Now, the tabulated t value is 2.306, right, and the observed value is not greater than the tabulated value. So, that means we accept the null hypothesis that beta 2 is equal to 0. Okay. So, accepting this null hypothesis means accepting the null hypothesis beta 2 equal to 0 means that the regressor, second regressor x 2 is not significant in the presence of x 1. Now, what we do next, what we will do is that we will test the significance of x 1 now in the presence of x 2. Well, the next one is what does x 1 contributes given that x 1 is already in the regression. That means, the significance of x 1 in the presence of x 2 in the model. This can be tested by testing the hypothesis that h naught beta 1 equal to 0 against beta 1 not equal to 0. Here is the test statistic value, here is the tabulated value. Again you see that the tabulated the observed value is not greater than the tabulated value. That is why we accept the null hypothesis beta 1 equal to 0. Okay. So, that means none of the partial F tests are significant, partial test or the t test, none of the partial tests are significant. So, what we observed here is that see the global F test is significant. The global F test says that there is a linear relationship between the response variable and the regressor variable, but when we go for the partial test, then none of the regressors are significant. Neither x 2 is significant in the presence of x 1 nor x 1 is significant in the presence of x 2. So, this is one example basically. If the global F test is significant, then at least there should be one regressor which is significant, but here we are getting the result the global F test is significant, but none of the partial tests are significant. That means, this might be the effect of multicollinearity. So, you can check whether multicollinearity exists in the given data. That means, whether x 1 and x 2 are linearly dependent, that you can check. So, this is one example of the effect of multicollinearity in the data, right. So, next we move to another effect of multicollinearity, that is that says that different model selection procedures yield different models. Okay. Okay. So, model selection means about the model selection. We talked about selecting the best model in module 3 perhaps. Well, we know how to select the best model using using the all possible selection and also the stepwise selection. Okay. Well, so what it says that if you have if there is the presence of multicollinearity in the data, then different model selection technique will produce different model. Okay. So, this is if you of course, different model selection procedure can yield different models, but if there is a multicollinearity present in the data, then the different, I mean, with high probability that the different model selection procedure will yield different models. Okay. So, these are the different problem that can occur due to multicollinearity we talked about. Next, we will be talking about the I mean, we will talk about the different techniques to detect the multicollinearity. Okay. Okay. The first technique is examination of correlation matrix X prime X. So, it says that simple measure of multicollinearity is inspection of off-diagonal elements that is Rij in X prime X. Okay, so we know what is correlation matrix given the original data. If you scale and center them, then the transform data or the modified data, the X prime X for the modified data is called correlation matrix. Okay. Now, the off diagonal elements of the correlation matrix is are Rij's, where Rij is the sample, I mean, is the correlation coefficient between the regressor xi and xj. Okay. Now, if regressor xi and xj, if they are dependent, then the Rij will be near to unity. So, that means if the regressor xi and xj, the correlation coefficient for the regressor xi and xj value is high, that indicates the presence of multicollinearity. So, as a general rule, we said that if Rij is the correlation coefficient between the regressor xi and xj. If this one is greater than 0.9, then it indicates Rij greater than 0.9 indicates multicollinearity problem. Now, examining the correlation matrix x prime x is helpful in detecting linear dependence between pairs of regressors. Okay. But the same is not let me complete but examining the correlation matrix x prime x is not helpful in detecting multicollinearity problem arising from linear dependence between more than two regressors. Okay, so let me explain what I wrote here. It says that the examining the correlation matrix is helpful in detecting linear dependence between pair of regressors, but the same is not helpful in detecting multicollinearity problem arising from linear dependence between more than two regressors. Well, so what it says basically, if the problem of multicollinearity is due to the linear dependence between two regressors, then the correlation matrix can detect that. Okay. If the multicollinearity problem is due to the linear dependence between two regressors, but it might be the case, say we are in the multiple linear regression setup. So, there are k minus 1 regressors and k minus 1 could be greater than 2, okay. But it might be the case that the the problem of multicollinearity is due to the linear dependence between more than two regressors. In that case, this correlation matrix can't detect the presence of multicollinearity in that case. Well, so let me give one example to illustrate this fact. I will be taking this data. It says that unstandardized regressor response variables from Webster, Gunt and Mason. Well, so I will refer this data as Webster data. Here we have 6 regressors response variable, and to check what I want to say here is that later on we will see that this data, I mean this data has the problem of multicollinearity, but the correlation matrix can't detect it, okay, because the multicollinearity problem in this Webster data is not due to the linear dependence between two regressors. Here we have linear dependence between the regressors involving more than two regressors. Okay. So, what we do is that first we will compute the correlation matrix for this data, and here is the correlation matrix. Here is the correlation matrix for the Webster data. You see the off diagonal elements here, none of them are suspiciously large. Okay. Here this is perhaps the highest correlation value. So, here we say that Rij, so this is R12, this is R13, we say that Rij, if Rij is greater than 0.9, that indicates this indicates multicollinearity problem. Okay. But here none of the pairwise correlations are suspiciously large, and we have no indication of near linear dependence. Okay. So, so here the inspection of Rij is not sufficient to detect the multicollinearity. So, the ultimate conclusion is that the examining the correlation matrix is not sufficient to detect the multicollinearity problem if the multicollinearity problem involves linear dependence between more than two regressors. Well, so next we will be talking about one more techniques to detect the multicollinearity. Okay. So, so the examining the correlation matrix is not sufficient always. Okay. So, next we talk about eigensystem analysis of x prime x. Okay. So, it says that multicollinearity can also be detected from the eigenvalues of the correlation matrix x prime x. Okay. I hope you know what is eigenvalue and eigenvector, associated eigenvectors. So, for a k minus 1 regressor model, this one is k minus 1 cross k minus 1 matrix. There will be k minus 1 eigenvalues, say lambda 1, lambda 2, lambda k minus 1. Okay. So, now you know if there are one or more linear dependence in the data, then one or more eigenvalues will be small. Okay. Basically, you know, if you have a small eigenvalues, that implies small eigenvalues implies that there is linear dependence between the columns of x. Okay. Now, we define the condition number, define the condition number of x prime x as k, which is equal to lambda max by lambda minimum. So, lambda max is the maximum eigenvalue and lambda minimum is the minimum eigenvalue. Now, you know that a small eigenvalue indicates linear, one or more small eigenvalues indicates one or more linear dependencies in among the regressor variable, okay, or linear dependencies among the columns of x. Now, look at the condition number here. If lambda minimum is small, or very close to 0, then this condition number is going to be large. And since lambda minimum if lambda minimum is small, then there is linear dependencies in the data. Okay. So, from there we can conclude that when lambda minimum is small, k is going to be large. So, the large value of k indicates the presence of multicollinearity in the data, right. So, we will give a general rule. So what is k? K is lambda max by lambda mean. As a general rule, k less than 100 indicates no serious problem with multicollinearity. Now, k in between 100 to 1000 indicates moderate to strong multicollinearity. And k greater than 1000 indicates a severe problem with multicollinearity. Okay. So, large value of k indicates the severe problem with multicollinearity, because of the fact that k will be large when lambda minimum is very small or close to 0. Well, and since lambda minimum is 0 indicates there is linear dependence among the columns of x. Okay. That means the presence of multicollinearity. Okay. So, this is the condition number. Now, we define the condition indices. The condition indices of the x prime x matrix are kj, which is equal to lambda max by lambda j, okay, for j equal to 1 to k minus 1. And of course, clearly the largest condition index is the condition number. So, this will be large when lambda j is minimum, and that is nothing but the condition number. Okay. Now, this eigensystem analysis, it's not only it not only detect the multicollinearity problem, also it can measure the number of linear dependencies in the in the data. Okay. So, that can be, I mean, the number of Kj or condition indices greater than 1000 is a measure of the number of linear dependencies in the data. Okay. So, the number of Kj greater than 1000, because if see if Kj is greater than 1000, then that indicates severe problem with multicollinearity. Now, number of Kj greater than 1000 is a useful measure of the number of near linear dependencies. In x prime x. Okay. If we consider the Webster data, the eigenvalues for Webster data are, so there we had 6 regressors. So, 6 eigenvalues, lambda 1 equal to 2.4288, lambda 2 equal to 1.5462, lambda 3 equal to 0.9221, lambda 4 equal to 0.794, lambda 5 equal to 0.3079, lambda 6 equal to 0.0011. So, this eigenvalue, the smallest eigenvalue is very close to 0. So, this one is basically just there is, we say that there is only one small eigenvalues. Okay. Small eigenvalues means very close to 0, and the condition number here also small eigenvalues indicates linear dependence in the data, one linear. So, since there is only one small eigenvalue, we can say that there might be only one linear dependency in the data, but of course, we have to check with the condition indices also. Let me first compute the condition number. The condition number is the condition number is k, which is lambda max is lambda 1 here, 2.4288 by 0.0011, which is equal to 2188.11, and this is larger than 1000, right. So, this indicates severe problem with multicollinearity. Okay, so what I want to say here today regarding the detection of multicollinearity problem is that, first we consider this Webster data, and examining the correlation matrix could not detect the problem of multicollinearity in the Webster data, whereas this eigensystem analysis technique, it says that since the condition number is 2188, which is much larger than 1000, so it says that there is a severe problem with multicollinearity in the Webster data. Okay, so not only this one, in the next class we will be talking more about, we will compute the condition indices, and from there we will see how many linear dependencies are there. Okay. So, that is all for today. Thank you for your attention.